As you can see, we're not even done halfway this semester yet, because after spring break starts the second half of the semester. So that's when the second 8-week courses start. So we really have 9 weeks of 9 week of classes left, which means we have 18. This one here, these are by 5, 10, 15, 18. So if we do one section a day, we'll be finished at the end of the semester. But like today, we're going to cover 2 sections because, I mean, a lot of these are quick and easy ones that we talk about. Fundamental theorem calculus, that's going to be a quick and easy one. Indefinite integrals and substitution method, that's also pretty quick and easy. Today we're going to do 2 sections. So, and the derivation of trig functions, really, that one shouldn't take us more than 5 minutes. Once I show you how it's done, you could apply it to all the trig functions. Because we know how to do the power rule, we know how to do the quotient rule, we know how to do the product rule. So that's all those really are. And then on Thursday, we'll do implicit differentiation and related rates are pretty much the same thing. Implicit differentiation is when you have x and y combined on the same equation. You don't separate them. You take a derivative with both of them with respect to x and y. And related rates, that is, for example, if you threw a pebble into a calm lake, what happens? All those circles, the consecutive rings, that's related rates. You can see once you measure the first couple of rings, you can measure how far it's going to be and how big it's going to be at a certain time period. That's related rate. Or if you want to make a box bigger, what would you do? So that's, again, all those just the same concept. So we really should be able to finish, if not all of chapter 3, then 4 sections this week. That'll get you ready for spring break. And then when we get back, we only have chapters 4 and 5. We have 8 weeks to do that. So we're in good shape. Well, let me put it this way. As a class, we're in good shape. Some of y'all got my progress report that you haven't even started chapter 2 yet. Or so there's some people who haven't done anything yet. But again, that's why I put the last day as the end of the semester to turn in things. Because maybe you have other stuff you want to finish, other courses, and try to get that finished. However you want to work it out. But make it known that there are no extensions. Once May 9th comes around, adios. So, all right. What we're going to do now, we're going to talk about the derivation of trig functions and their derivatives. The derivation, actually, I meant to say the derivative of trig functions, derivatives, yes. We didn't? What's 3.4? Mm-hmm. Yeah. If not, then I'll do that later on. Yeah. I mean, really, a lot of these things are not sequential in this. Just have to know this in order to do this. It's like trig functions. So we can pop that up anywhere we want to. So, but I want to get these things done as fast as we can. All right. To begin with, the only thing you really have to know about the trig functions is the unit circle, because at each of these locations, x negative y. So that's the unit circle. Remember what the coordinates were on the unit circle? What's this one here? 1, 0. Now you're 0, 1. And this one? Right. So that's where it's far. Also, we have to know these 6 trig functions. If you know those 2, you know the other ones. Tangent x is what? Sine over cosine. Then we have the inverse functions. We have secant, cosecant, and then cotangent. What is secant? No. The easiest way to remember these, because you're right, these are both 1 over. You cannot have the same first letter. So it cannot be sine. So the other one has to be cosine. This one's C, so it has to be sine. That's the way I remember. And cotangent is 1 over tangent, which is cosine over sine. See, so if you know sine and cosine, you know them all. You could do the work to figure them all. So another thing we have to remember is the cosine function deals with which axis? The cosine function references and refers down to the x-axis. So no matter where you are, it refers back down to the x-axis. And then the sine then is which could be seen in the unit circle. At this point here, it's 1, 0. Each point is made up of a cosine and a sine value. The cosine is the x, sine is the y. So at 0 degrees, we have cosine equals what? At 0 degrees, sine equals, yeah, and so on and so forth. At 180 degrees, cosine equals -1 and sine equals 0. So once we know that, and here's the that's trigonometry. That's not even calculus yet. Calculus deals with derivatives and integrals. I know we haven't done integrals yet, but let me show you how it is. So taking this unit circle, since the cosine is 1 here, sine is 0, we don't worry about it. Don't worry about the sine. The cosine is 0 here, sine is 1. Because if the value is 0, we don't need to know about it. And also, cosine deals with the x, sine deals with the y. The derivatives. These are the derivatives. So the derivative of sine is what? Cosine. The derivative of cosine, negative sine. The derivative of negative sine is negative cosine, and so on and so forth. You keep on doing that infinitely in circles. Once you remember that, taking derivatives of trig functions, no problem. As long as you remember to do the product rule, the quotient rule, the power rule, whatever it takes. So those are the derivatives. Eventually, the last part of this course, we're going to go backwards. So from the integral of sine is negative cosine, because integrals go backwards. This just pretty much saved you a couple of days of lectures. Because you look at that sheet I gave you, you have the first derivative. It doesn't explain, well, I could prove to you why, but we got to use the sum and difference identities. and then take the derivatives or limits as h goes to 0 of these functions, and it won't give us too much help. So there we have it. That's the derivative and integral chart. That's all you need to know. Let's look at our first example. Example 1. A. Y equals x squared minus sine x. Find the first derivative. What rule are you going to use here? Because these are addition subtraction, you could do them in individual pieces. You could take the derivative of this one and the derivative of this one and subtract them. So what's the derivative of x squared? 2x minus the derivative of sine x. And there you have it. That's the first derivative. Again, I need you guys to memorize all those rules of derivatives. The product rule, the power rule, the quotient rule. Because if you don't know those, this is going to take you forever to do. When I asked you what was derivative of x squared, you should just spit out. It's automatically 2x. Because how do you get the derivative? The power goes down and you subtract one from it. That's the power rule. Again, I need you guys to go through and review these. B. Y equals e to the x sine x. So this is a product. So we use the product rule, which is you find f prime g prime, and do the fish. It's going to be g times f prime plus f g prime. E to the x that. And all the thing we factor out is the e to the x. Same thing here. What is this? What property are we going to use here? It's a fraction, so it's a quotient. It's a quotient rule because there are x's on top and x's on the bottom. If I had sine x over 3, would we still use a quotient rule? No, because there's no x. It's the same as 1/3 sine x. So the f is the sine x, and g is the x on the bottom. The derivative of sine x is cosine x. The derivative of x is 1. Since it's a quotient, we subtract. G f prime minus f g prime, and you square whatever's on the bottom. And there you go. That's your derivative. What's the derivative of that? Buddy, it shouldn't take that long because this equation is the same as 3/4 times sine x. This is a constant multiple. So the derivative of sine is cosine. So the answer is 3/4 cosine x, or 3 cosine x over 4. How many of y'all started doing the quotient rule? What's taking so long? Because there's not much there. Because there's no x's on the bottom. It can't be quotient. There's no x's on the bottom. We only have one x. That's right there. So be careful because you'll see a bunch of these type of equations that look difficult, but they're really just a single term. Because I can also give you something like this. Find the derivative of this. Okay, the rules of algebra. How many of you, what rules of algebra are you following here? What's the first thing you're going to do? Because we're looking for the derivative. How many of y'all try to find the LCD first? What did everybody do then? What was everybody writing down or taking the last 5 minutes doing what? Okay, so that took 2 seconds. Close. Yes, that is a derivative of sine. But the rule is this: if you have a monomial on a fraction, I can split them up. So whenever you have a fraction over a fraction, what do? Take the top fraction, leave it alone, and multiply by the flip of the bottom. So we can rewrite y These cancel. So we have 1/6, 5/8. Now we take the derivative. The derivative of a constant is what? 0. This is a constant multiple. So now we take the derivative of sine, which is cosine. I know it looked pretty ugly when I first put it up there, but when you put it down this way, you only worry about the parts that are x's. Because if it doesn't have an x, it's a constant. So far, so good. All right, so we talked about the derivative of sine. Derivative of cosine is what? The derivative is what? Negative sine. Look at your chart. Look at your table. And if you don't remember it, draw the unit circle and put the x's, cosine on the x's, sines on the y's. And you go clockwise for derivatives. So looking at example 2. We have 5e to the x plus cosine x. We want the derivative. Since these are added together, we do each one separately. What's the derivative of 5e to the x? Doesn't change. Because that's a constant multiple. The derivative of e to the x is e to the x. The derivative of cosine is, and there's your answer. B, y equals sine x times cosine x. This is the product rule because we have f times g. So we have f times g, f prime, g prime. The derivative of sine x is cosine x. Derivative of cosine is negative sine. So since it's a product, we increase it. So cosine times cosine plus sine times negative sine equals cosine squared x, positive, negative, minus sine squared x. And there you have it. You see how if you did anything wrong, you see what you did wrong? What was the most common mistake you did there? We got it? All right, let's look at C. y equals cosine x over 1 minus sine x. Quotient rule. We have x's on top and bottom. Cosine of x, 1 minus sine of x. The derivative of cosine is negative sine. The derivative of 1 is 0 minus derivative of sine, cosine. So it's a quotient rule. So we subtract. So we have 1 minus sine x times negative sine x minus cosine x times negative cosine x, all over 1 minus sine x squared. Whatever's on the bottom, you square it. Now we do the algebra part. We have negative sine x plus sine squared x plus cosine squared x over 1 minus sine x squared. So far, so good? I distributed this one to both of those. Negative is a positive, cosine squared x. Now, if we remember our trig rules, our trig identities, we have negative sine out here. What is sine squared x plus cosine squared x? Plus 1. It's an identity. Over 1 minus sine x squared. By the commutative property, I could rewrite the top part. I can move the 1 minus sine x over 1 minus sine x squared. Can anything cancel? 1 minus sine x. So we end up with 1 over 1 minus sine x. This is our derivative. What do you mean factor out?
There's sometimes you hit with the square.
Well, only if something cancels can we, because you usually don't touch the bottom. But because the top was 1 minus sine, this is on the bottom, we have 1 minus sine times 1 minus sine, they cancel. We're just simplifying, we're not changing anything, we're just simplifying it. But yeah, you're right. Typically, we never touch the bottom unless it's this obvious. We change it, we just simplify it. Any questions? You have to practice your quotient in your product rules. There's no way you can learn it if you don't do it. Because it looks easy when I do it. Or confused when I do it. Example 3. Now we're going to look at some application problem. This is called a simple harmonic motion problem. Harmonic means it follows a pattern, like the sine and cosine wave. If you remember what the sine and cosine function, the graphs look like, So let's look at the cosine function. At 0, what is cosine of 0? 1. Cosine of pi over 2? Yeah. Make it easier for you here. This is 0 degrees. This is pi over 2. This is pi. This is 3 pi over 2. And that complete circle is 2 pi. So cosine of 0 is 1. At pi over 2, it's 0. At pi, it's -1. 3 pi over 2 is 0. And at 2 pi, it's back to 1. So this graph follows this curve forever. What does the sine function look like? At 0, what's sine? At pi over 2? At pi? At 3 pi over 2? And at 2 pi. So the sine function follows this repeated pattern. That's what we call a harmonic motion, because it follows the same pattern up and down. Now, how does this relate to springs? If we looked at a spring bobbing through time, the x-axis is always time. At rest, the, the, the spring doesn't do anything. If you pull it down, let's say 3 inches and let it go, what happens? It will rebound up the first time pretty close to 3, and then it'll dampen down because of heat resistance and friction of the air. So our graph will look something like this. As time goes on, this graph, of course, eventually it's what we call dampens, tapers off, but it has a harmonic motion. So example 3 looks just at that. A weight hanging from a spring, shown below, is stretched down 5 units beyond its resting position and released. At time equals 0. To bob up and down, the position of the function can be represented as, first off, I'm going to ask you, why, okay, S in physics is the position function. It's actually S of t. The position of the function, the position of the object y5. That's our 5. Yeah, we put it down 5 units. So that was our initial position at time equals 0. Why cosine? Because the horizontal axis is time. And that's the only thing that changes. So everything we look at is in reference to time. Time is the x-axis, which is the cosine function. So that's where we got that. What this thing's asking, what are its velocity and acceleration at time t? What are its velocity and acceleration at time t. I'm also going to include example 4 in this one. Example 4 is saying, what is the jerk of the spring object? Now we have to look at this. What does a derivative represent? The derivative represents rate of change. Position function is where an object is at one time to where it is the next time. That's just the position of the function. The first derivative, velocity, is the first derivative of our position function. So v is equal to s prime. We know that s of t equals 5 cosine of t. So what is the velocity? So what's the derivative of 5 cosine t? Negative 5 sine of t. Because the derivative of cosine is negative sine. It's a constant multiple. You don't do anything with that. Leave it at that in front. Just take the derivative of cosine. When we deal with trigonometric functions, we always talk about amplitude, or we're doing a phase shifting, and periods. So in our original function, our position function, what's our amplitude? What does amplitude mean? Maximum what? How do you mean? T goes on infinitely. Or you're not talking about T. Amplitude is the height. What is the highest point reached or lowest point? We're looking at the absolute value. So the amplitude is 5. That is the amplitude. What is the period of cosine function? What's the period of cosine? What does period mean? What do you mean? Not intervals. Or you could be interval. How do you mean interval? That's another one. What's that? How long until the graph or the function repeats itself? That's a period. But yeah, you look at that. But in other words, if we look at our graph, cosine, it starts off at 1 here. The next time it's 1 is at 2 pi. So our period is 2 pi. Our amplitude is 1. when we stretch the spring, we now have 5 as our amplitude. That's what we usually look at the absolute value of it. So the period is 2 pi. Now, what does this tell us? At what point t is the greatest, does this give us the greatest value? The greatest change of velocity? At time equals 0, what's the sign of 0? 0, 0 times, that's 0. That's not the greatest. Basically, since it's -5 here, when is sine -1? 3 pi over 2. So at 3 pi over 2, that's when the velocity is the greatest. Actually, what's happening is it's going to the greatest, because what happens at the top of the curve? What is the velocity there? Why is it 0? What's that? Well, yeah, because here the velocity is positive, it's increasing, and here the velocity is negative, it's actually decreasing, it's going back down. Someplace between there, our slope is 0. Remember, derivative is a slope. So at 3 pi over 2, and at our velocities are 0. Okay, so that's the velocity function. What is the acceleration? Acceleration is the rate of change of the velocity of the object. So velocity is the rate of change of the position. Velocity is the rate of change of the velocity. Acceleration is change of velocity. So if we have to find the acceleration, that is the first derivative of a velocity. But this also means it's the second derivative of our position function. Because velocity is the first derivative. If we take the derivative of velocity, that means we're taking the derivative of a derivative. So what's the derivative of -5 sine t? The velocity is -5 sine t. What's the derivative of -5 sine t? -5, because it's a constant. Derivative of sine is cosine. Very good. So in here, we can see where the velocity, where the acceleration changes. And that's what example 3 was looking for. Now, example 4, it says the jerk. The jerk is the rate of change of the acceleration of the object in motion. So the jerk is the first derivative of acceleration, which is the second derivative of velocity, which is the third derivative of our position. So what is our jerk? Yeah. Very good. 5 sine t. Those are them. Do we have any other examples? Oh, yes. All right, let's look at the other trig functions. The derivatives of the other trig functions. So tangent. If y equals tangent x, what is its first derivative? Tangent is made up of sine over cosine. So we got to use the quotient rule. Derivative of sine is cosine. Derivative of cosine is negative sine. Since it's a quotient, we subtract cosine times cosine minus sine x times negative sine x all over the denominator squared. Cosine times cosine is cosine squared x. Negative times negative is a positive. Sine times sine is sine x over cosine squared x. Cosine squared plus sine squared x is 1. So our derivative, 1 over cosine, is secant squared. Let's look at the derivative of cotangent x. You got a question? You have a question?
Oh, wait, I'm sorry, I forgot the- How does it? Why does it cosine 2x over 2 cosine 2x? Why does it not cancel?
Can anybody answer that? If I had 2 plus 3 over 3, that's 5 over 3, right? If I cancel these, what would I get? You guys missed that too. Because if you cancel it, you get 1 left over. So it'll be 2 plus 1 is 3. That's not the same. Because you have a plus or minus, that has to be kept together. Good question. That's the most common mistake because people really don't understand that concept. All right. Yeah, we have quotient rule again. Derivative of cosine is negative sine. Derivative of sine is cosine. Sine times negative sine minus cosine x over sine x squared. Negative sine squared x minus cosine squared x over sine squared x. So far, so good. What do the top have in common? They both have a negative. So I factor out a -1, which will give me sine x plus cosine x squared. Which leaves us at -1 over sine squared x, which makes it negative cosecant squared x. Again, as I told you earlier, calculus is simply it's the first domino you push. The rest of those dominoes fall from algebra and trig. How well you know those will pretty much make or break you in calculus series. So I can't stress enough, bless you, to go through and learn as much as you can about the review your algebra. All right, let's look at cosecant and secant. Let's do cosecant. What is cosecant? 1/sine. Yep, so you can't have the same first letter. The derivative of 1 is 0. The derivative of sine is cosine. So we have 0 times sine minus 1 times cosine. All over the denominator squared. Are we done? No. Identities. Because we have the sine squared on the bottom, I can split that up into two functions. Cosine over sine is cotangent. 1/sine is cosecant. And that's your first derivative. And the last one is going to be similar, the secant function, which is 1 over cosine. The derivative 0, negative sine. Hopefully, the more you do this, when you see cosine, sine, the derivatives, you can just do those real quick. So 0 times cosine minus 1 times negative sine over cosine x squared. So that's 0, negative, makes it a positive. So it's positive sine x over cosine squared x, which is sine x over cosine x times 1 over cosine x. Sine over cosine is what? Tangent x, 1 over cosine. And there's your derivative. Once we've proven these, now instead of if you have your cheat sheet, you can just jump straight to it. But you have to know how to do it just in case you don't have a cheat sheet. So example 5 is do the derivative of tangent, which we've just done. Example 6 says find if y equals secant x. So what is this one asking you to find? Or the second derivative. Find the second derivative of secant. Fortunately, we took the first derivative already. What's the first derivative of secant? What's that? Right. Tangent x, secant x. Yay, we did the first part. Now we have to do this derivative, which means now we have a product rule. The product tangent secant. The first derivative of tangent is what? Secant squared x. The derivative of secant, which we just did, is tangent x secant x. So it's the product of that. Got it down here. So it's going to be secant x times secant squared x. Since it's a product, we add tangent x secant x. So far, so good. Secant times secant squared is secant cubed. Tangent times tangent is tangent squared secant. That's your answer. Oops, secant x. Yeah, I mean, you trust me. The more you do this, the better you'll get. The faster it'll all become. And you have to know how to do your trig identities, trig functions. Do you want me to go through and review the trig identities? Okay. The trig identities all start from this formula. Because if you think about it, A, B, C, where A is the x-axis, horizontal axis, so that's cosine. The vertical axis is the y-axis, so that's the sine. And our unit distance is 1. That's where it all begins. This is our first one. Now, for our second identity, divide by cosine squared x, each term, which is cosine squared x over cosine squared x, sine squared x over cosine squared x, 1 over cosine squared x. This becomes 1. Sine over cosine is tangent squared x. 1 over cosine is secant squared x. This is our second identity. And then the second, we go back to the original, and divide them by sine squared. Cosine over sine is cotangent plus 1. 1 over sine is cosecant. And this is the connection between all of them is they all can equal 1. All of these are the same thing. They all equal 1. That again, it all started off from a Pythagorean theorem because we deal with right triangles. So those are the identities. Again, knowing these will save you a lot of time also. It may be easier to do derivatives or integrals with these. Example 7 simply says, if we're taking the limits of trig functions, we can use direct substitution. So if we take the limit as x goes to 0 of radical 2 plus secant x cosine pi minus tangent x, the first thing you always do when you have a limit function, plug it in there. Radical 2 plus secant 0 cosine of pi minus tangent of 0 secant is 1 over cosine, which becomes what? Cosine of 0 is what? That becomes 1. Then we have cosine. Tangent of 0 is sine of 0 over cosine of 0. which is 0/1, which is 0. On top, we have 2 plus 1 is 3, radical 3, over cosine of pi. Cosine of pi is -1, because pi is over here. So it's radical 3 over -1, which makes it negative radical 3. So again, with limit functions, first thing you always want to do is just plug it in there. If it works, it works. If it doesn't, then we do something algebraic. All right, that does it for that section. Let's go to the next one. We have time. Plenty of time. The next one deals with the chain rule. This is going to be important. Oops,